Field effect transistor is abbreviated as FET or FET. It is a three-terminal unipolar semiconductor device in which the output current is controlled by the voltage or the electric field applied at the input terminals. It is called a unipolar semiconductor device because in the case of FET, the current is either carried by the electrons in case of n-channel FET, or it is singularly carried by the holes in the case of p-channel FET. Since the current carrying charge carriers are of a single polarity, hence these devices are called unipolar semiconductor devices. The other type of transistors which we have dealt earlier and are categorized as NPN or PNP transistors, they are the bipolar devices, and in that case the output current is controlled by the input current. That is, the collector current is controlled either by the emitter current or the base current, depending which terminal we are taking as the input terminal. These devices, NPN or PNP transistors, are named as bipolar transistors because in these transistors the current is carried both by the majority and the minority charge carriers. If the majority charge carriers are electrons, then the major current which is being carried by the electrons, there is a minute current in the transistor which is being carried by the minority charge carriers or the holes. Similarly, if the majority current is carried by the holes, then the minority current will be carried by the minority charge carriers, that is electrons. Therefore, they are named as bipolar semiconductor devices. And in this case, the output current in this figure, the construction of field effect transistor is shown. There are two types of JFET. This is the P-channel JFET and this is the N-channel JFET. If we are considering the P-channel FET, then the channel is made of P-type semiconductor and it is very lightly doped. In case of N-channel FET, the channel is N-type semiconductor which is very lightly doped. On the two sides of the channel, in case of P-channel FET, N-type semiconductor is diffused and these two portions are called gate of the P-channel FET. These two portions are heavily doped N-type semiconductors, and in the case of N-channel FET, on the two sides of the channel, P-type semiconductor is doped and this is the gate region, and as in the case of P-channel FET, here also the gate region is heavily doped. A terminal is taken from this portion or this side of the FET, and this point is called the source and this terminal is called the source terminal. On the opposite side of the channel, a terminal is taken out and this point, this contact point is called the drain and this terminal is called the drain terminal. These two gate portions or the gate regions are interconnected and a single terminal is taken out which is called the gate terminal. Similar is the case with the N-channel FET. Now in figure number 2, the symbols of N-channel FET and P-channel FET are shown. The channel in the symbol, the channel is shown by a single vertical line. This is the source terminal, and on the opposite side is the drain terminal, and in between there is a gate terminal. In case of N-channel FET, in the symbol we can see that in the gate terminal an arrow is placed, and the direction of the arrow shows the direction of flow of the positive charge or the conventional current. If we see the N-channel FET, since we are considering the symbol of N-channel FET, so we will go to the construction side of N-channel FET. In this case, the gate region is P-type semiconductor and the channel is N-type semiconductor. So in the case of N-channel FET, the positive charge is present on the gate. So whenever there is a flow of positive charge, so it will flow from gate towards the channel. Positive charge will flow from gate towards the channel. Therefore, in the symbol of N-channel FET, the direction of arrow, which shows the direction of flow of the positive charge, it will be from gate towards the channel. If we consider the P-channel FET, then the channel is P-type semiconductor, and the charge will flow from the channel towards the gate. Hence, if we are considering the symbol of P-channel FET, then the direction of arrow will be from channel towards the gate. Hence, the direction of arrow is from the channel line towards the gate. So, this is the symbol of P-channel FET, in which the direction of arrow is from channel towards the gate. Now we will study the formation of depletion layer in a junction field effect transistor. We know that when an ordinary PN junction is formed, due to the diffusion of charge carriers, a depletion layer is formed on the two sides of the junction. We know that on the P side, the holes are the majority charge carriers, and on the N side, electrons are the majority charge carriers. When a junction is formed, the electrons from the N side cross over to the P side due to the attraction towards the holes, and the holes on the P side, they are attracted towards the electrons on the N side, so they cross over to the N side of the semiconductor, and whenever there is a crossing over of the charge carriers, recombination of charges takes place, and due to the recombination there is some loss of free charges, or there is some shortage of free charges on both sides of the junction. Due to this shortage of free charge carriers, a narrow layer is formed on both sides of the junction, which is called the depletion layer. And we know that in this depletion layer, there is a shortage of free charge carriers. There are some important properties of the depletion layer. The first is that if the reverse bias across the junction is increased, then the width of the depletion layer increases. We are not going into the details of these properties, because only knowing that this increase in the reverse bias will increase the width of the depletion layer, our purpose of discussing the working of FET will be fulfilled. And the second is that if the doping on the two sides of the PN junction is unequal, that is, on one side the doping is light and on the other side the doping is heavy. Doping means the concentration of impurity. If the doping on the two sides is unequal, then the depletion layer has a larger width on the side in which the doping is light, and the width of the depletion layer is small on the side where the doping is heavy. It means that on the lighter doping side, the width of depletion layer will be more, and on the side of heavier doping, the width of depletion layer will be narrow. Now this was a discussion about the depletion layer of an ordinary PN junction. Now we switch over to a FET. This is the construction of the FET. This is the channel and this is the gate region on one side and this is the gate region on the other side. As there is a junction of P side and N side or N type of the semiconductor, so along the junction line of the P type and N type semiconductor, a depletion layer will be formed on both sides of the junction. This is the junction line. Depletion layer will be formed on the gate side as well as on the channel side. But we know that the channel is lightly doped and the gate region is heavily doped. Therefore, a depletion layer will be formed on both the sides, but the width of the depletion layer will be narrow on the gate region of the FET and on the channel side of the junction, because channel is lightly doped. Therefore, the width of the depletion layer will be more. Similar is the case on the other side of the gate region. Depletion layer will be formed on this side of the channel also. So this is all about the formation of depletion layer in a junction field effect transistor. And we know that if as we will see further in the forthcoming slides, if we apply a reverse bias uh, between the gate and the source, then the width of this depletion layer will be increasing, because with the increase in reverse bias, the depletion layer width increases. Now we come to the actual working of junction field effect transistor. Before discussing the working of a FET, we will discuss how the gate and source junction and source and drain junction are biased, or a voltage is applied on these two junctions. First, we will consider the gate and source junction. One thing is very important with the biasing of gate and source junction. This important point is to be noted forever when we are dealing with the FET, that the gate and source junction of a FET is always reverse biased, because the gate and source junction is the input junction, or these are the input terminals of the FET, which is going to control the output current. We know that a FET is a voltage control device, that we have already discussed, that the output current of a FET is being controlled by the voltage applied at the input terminals. So we will see that the voltage which is being applied between the gate and source will have a control over the output current. And to make this control more effective, the gate and source junction is reverse biased. In the further discussion in forthcoming slides, we will see how this reverse bias which is being applied on the gate and source junction will have a control over the output current or the drain current. So we can say that the gate and source junction is reverse biased. It means that when we are considering the n-channel FET, the gate portion or the gate region is p-type. So this gate and source junction, that is this side is P and the source terminal or the source region is n-type. Therefore, we will connect the battery or the source of voltage in such a manner that P side is negatively biased and the this N side or the source terminal will be given the positive potential. The gate is negatively biased and the source is the positive polarity of the voltage source is given to the source terminal. Therefore, in this manner, the gate and source junction is reverse biased. And we know that a depletion layer is formed, as we have discussed earlier. A depletion layer is formed along the junction line of this PN junction. A PN junction is formed between the gate region and the channel. Therefore, a depletion layer is formed like this. And we know that, and we can make out that this depletion layer or the width of the depletion layer is uniform along the junction line. And this depletion layer is formed on the other side of the channel like this. The depletion layer is formed on both sides of the channel along the PN junction. Now we have to see what is the effect of this variation in the gate source voltage on the depletion layer. A uniform depletion layer is formed on along the junction line, and if we are increasing this reverse bias, we know that when the reverse bias applied across a PN junction is increased, the width of the depletion layer increases. So if this reverse bias is increased, then the width of the depletion layer will be increased. In this case, there is the reverse bias has a smaller value, so the width of the depletion layer is smaller. And in the next figure, the value of this reverse bias is increased. Therefore, the width of the depletion layer is increased to a larger extent like this. And in this particular or this specific case, the value of this reverse bias is too large, and it has the depletion layer is increased to such an extent that the depletion layer on the two sides of the channel, they are touching each other, and the width of the channel or the passage from one side of the channel to the other side of the channel is completely blocked. This is the case when the reverse bias is excessively high. In the last slide, we discussed how the gate and source junction is reverse biased in a junction field effect transistor. Now we will discuss how the drain and source junction, or how a voltage is applied between the source and drain of a junction field effect transistor. In this figure, we are considering the n-channel FET, and as we can see from the figure, the source is connected to the negative terminal and the drain is connected to the positive terminal. When the battery is connected in this manner, it facilitates the flow of electrons from source towards the drain. We know that this is the n-channel FET and the majority charge carriers are the electrons. So when the source is connected to the negative terminal, then the majority charge carriers, that is the electrons, will be repelled by the negative terminal and they will be attracted towards the positive terminal. So there is a continuous flow of electrons from the source towards the drain, and a current will start flowing. The electrons are flowing from source to drain. Therefore, the conventional current, that is a positive charge, or we can say the direction of flow of the conventional current, is along the opposite direction or from the drain towards the source. This is the direction of drain current or the conventional current. Now we will see what is the effect of connecting the voltage source in this manner on the width of the depletion layer. We know that a depletion layer of uniform width is formed along the junction line inside the channel. The junction line of p-type and n-type semiconductor, which is formed inside the FET. There is a uniform depletion layer which is formed inside the field effect transistor. Now, when we connect this voltage source VDD and a conventional current is flowing along this circuit, this positive charge, since this is a direction of flow of positive charge, this positive charge is flowing across the channel. And suppose this channel resistance is RD, because whenever a current is flowing in a particular region or a particular semiconductor or a metal, it faces some opposition or the resistance. Suppose the channel resistance is RD and this is the direction of flow of positive charge. So some potential drop will be produced across this resistance. As we are considering the flow of positive charge, this is the conventional current. So the conventional current is entering this resistance from this end, and the conventional current is coming out of the resistance from this end. So the end of the resistance or the end of the resistor through which the positive charge is entering will be of positive potential. It will be at a higher potential, and the end of the resistor from which the positive charge is coming out, that will be at a negative potential. Hence the potential drop will be produced along the resistor RD, of which the upper end is at higher potential and the lower end is at a negative potential. Since this is a n-type semiconductor, so this end of the n-type semiconductor has a higher potential, and this end of the n-type semiconductor is at a negative potential. And when the n-type semiconductor is at a positive potential, then it is deemed to be reverse biased. Hence, at this end of the channel, the PN junction has more reverse bias, because at this end the N channel is at a positive potential, so there will be more reverse bias, and on this end of the channel the N-type semiconductor is at a negative potential. Therefore there will be a sort of forward biasing. Therefore this end has a slightly forward biasing and this end has slightly more reverse biasing. Hence we can say that the uniform width depletion layer, which was already formed across the or along the PN junction, it is slightly deformed on this side as the reverse bias is more. Therefore the width of the depletion layer will increase, and on this side of the depletion layer, as there is a sort of forward bias, hence the depletion layer which was already formed will get narrower due to the forward bias. Hence, the upper side of the depletion layer is swelled up, and the lower side of the depletion layer has become narrower. So the final shape of the depletion layer is like this. The upper side has more width and the lower side has narrower width, and this special kind of depletion layer is known as wedge shaped depletion layer due to its specific shape, due to the presence of the biasing battery, that is VDD.